All right. Okay. Right. Now we said that we will calculate this expectation by first conditioning on the number of arrivals until time t. We did that here, so we have to take care of this. Right? For any given fixed n, what is this conditional expectation? So let me copy that here. And this is the sum as k goes from 1 to n for the kth arrival time. Right? I get $1, therefore its present value is given by this. Given that there are in fact, or actually, exactly n arrivals. Right? Now we have this result that says if you denote by u1 through un, okay, independent, identically distributed, uniform 0t random variables. Okay. And if we further use as before, you want to denote the smallest of all these n random variables, and if u2 to denote the second smallest, okay, and the un the largest of all, then we can write this as the unconditional expected value of e to the minus beta times u kth, well, e to the minus beta times kth ordered statistic, right? And we sum over all these ordered statistics you have. So these are the same. These are the same because of this statement. They say the condition on xk, we even know more than just what this says. Right? Condition on the number of arrivals, the joint distribution of these random variables is just the same as the joint distribution of UKs. When you take expectation with respect to that conditional expectation, it is the same if you just take conditional expectation with respect to joint distribution of these ordered statistics. Therefore, these are the same. Okay? So then what happens? Now, does the problem get any easier? Well, you still have, you know that they have this, okay, they not only have the same distribution, you also know that what the joint distribution is. Are you supposed to use the joint probability density function of these guys to take this expectation? That's one way to do. And the other thing is just to note that does this sum, the value of this sum, depend on the order in which you sum these quantities as k changes? It doesn't, right? It doesn't. In fact, before you take expectation, now you see that this is the same as the sum of e to the minus beta times just uk, right? So I don't have to remember whether this uk is the smallest or the second smallest or anything. Every time I come across, one of those values will eventually come across, we will come across one of those values, we'll multiply with beta, take minus, and then raise to the power of this number e, and then sum. These two sums are the same, right? And therefore the expectations are the same. Right? And, well, now I guess it is easy to calculate this expectation. It is expected value of sum of random variables. Therefore, this is sum comes out of expected values of these random variables. Right? I could have done the same thing here as well, but then see, calculating this expected value is a lot easier than this one. Here we know the UK has a uniform distribution over interval 0t. Here it is a lot more difficult. Even I didn't state what it is. But as I said, who cares, right? Because this is, if it is easy to calculate this, and if you know that they are the same, why would you take the difficult role? And okay, let's calculate it. Yes.
What we have changed in the second line to third lines?
From here to there? Well, what is this? This is the kth smallest. Kth smallest of u1 through un, right? Actually, that was my point. Actually, nothing has changed here. They are the same, right? But if I want to take expected value of this, then I have to first calculate the expected value of this quantity. For that, I need to know the marginal distribution of UK, and it is a lot more difficult than UK. What is the probability density function of UK? Probability that UK is going to be somewhere near U. So what is this? These are uniformly distributed over the interval 0 to t. So you pick a U value, right? So there is this interval starting from U of length du. What was this? This is du over t. And what is this? Do I remember that? I should first ask that to myself. I guess we can derive that. Okay. So what is the meaning of this? The kth smallest of all these n variables is just in the neighborhood of this u. Right? That means k minus one of them should be on the left hand side of u, and one of them is just in this small interval. How many left to the right of u? N minus k. That's it. N minus k. Right? And so we know that. Okay, this is the same. It is. Is it the same? Is it the same as this one? Okay. Okay. Since the random variables are all independent of each other, right? Any one of k minus one of them should be on the left. Any one of n minus k of them should be on the right. Right? And then we will just, since all of them are independent, we'll multiply these numbers. Right? So you choose out of n, k minus 1 of these u1 through un, any k minus 1 of them, with probability u over t, they will all be on the left hand side of u. How many of them? K minus 1. And then you choose from the remaining, how many has remained? N minus k plus 1. How many do we have to choose? N minus k. We choose n minus k of them. I hope I am doing this right. Okay. And these are all supposed to be where? To the right of u, which is which can happen with probability t minus u, the length, right? They are uniformly distributed, you remember. So the probability that any one of them is going to be in this interval is what? Proportional with the length of that interval, which is t minus u. T minus u divided by t will give you 1 minus u over t to the power, how many we said? N minus k. And one of them should be right in this interval, which has length du, right? And that can happen with probability length is du divided by t. Okay, that's the density. And we can just simplify it. What is this? This is n factorial divided by n minus k plus 1 factorial times k minus 1 factorial, right? And this should be a lot easier, right? What is that? It's just one less. Is it supposed to be, it is like the 3 choose 2, which is supposed to be just this number. But I am not going to leave anything to chance. Right? Right? 1. Right? Is this correct? So I just combine this two. So this will cancel. No, that's too fast. Right? N minus k plus 1. Okay. Factorial. Okay, this factorial will get cancelled with this. Right? Why? N minus k plus 1. Right? So that remains like that. And then one of them is going to cancel this one, right? So this is going to be n minus k factorial. So then let's just write the... So it is n factorial divided by n minus k factorial times k minus 1 factorial times u over t to the power k minus 1 then we took care of these two, therefore only this was left. Okay. So k minus 1 shows up here, n minus k shows up here. Okay? Which makes sense. And this also has an interpretation. What is this? It is like, okay, you fixed a reference point to you, right? There is a point u, you know that exactly k minus 1 should be on the left, and each one of them is going to be on the left with this probability. Therefore, you raise to the power k minus 1, and minus k one of them should be on the right. So you raise to that power the remaining probability. And then you shuffle them in how many different ways? If you don't look at where they fall, you can shuffle all of them in factorial different ways. But those who are here, if you shuffle them within inside, you are actually getting the same event. Because you wanted exactly k1 minus 1 of them to fall here. Every time you just change the order of any two values that are already on the left, you are not getting actually something new, you are actually double counting. To just cancel those double counting, you divide by k minus 1 factorial. Because you can just shuffle k minus 1 of these u's on the left u in k minus 1 factorial different ways. We divide by that number to cancel out all the repetitions that are already inside n factorial. Well, something similar happens here as well. N minus k one of them will be shuffled actually within themselves. We have to divide by this n minus k factorial. The number of times, different ways you can shuffle them to cancel all those double counts. Even more than double actually, this many times. Right? You get this. Right? So tell me, is this pretty or this one? Huh? This is pretty actually, but you will not want to take any integrals with this guy. If you want to calculate this expected value, so what is this expected value? It is the integral of e to the minus beta u times this guy. Well, there is a du somewhere, right? du. So there is du. Oh, there is a t as well. Sorry. Right? This times that integrated from 0 to t. Well, this is pretty, but the integral is ugly. But here, if you want to calculate the expected value of this, it is only what? E to the minus beta u times this, which is dut. Right? Which you know by heart what it is, so you don't even need to calculate it. Right? So that's why we care so much about this result. So going from here to there is important. That's what the result says. Then we just notice that the sum of all these terms do not really depend whether you first sum, whether you add the seconds, you add this expression for the second smallest to the same expression for the smallest. Right? It doesn't matter in which order you sum all these quantities, because sooner or later all these ui's will show up over one of these powers and you are just summing them up. So therefore this sum is the same as this one. You don't have to remember which one is smaller or which one is the largest. Are you following me? Huh? Does this make sense? Huh? So these two sums are the same, so I can safely forget about, or just don't have to pay attention to the order. And then I said that I'm doing this because I'm trying to avoid calculating this integration with respect to this difficult density function. But I was successful in avoiding that, and then, well, I realized that this is a lot easier expectation to calculate. Yes?
If we are not adding all of the n's, for example, the upper bound n minus
Yes.
k, then we should use
Yeah, then maybe there is another way of doing it. But yeah, but this is not going to just translate. Yeah, then we have problem. We have problem with that. Actually, in one of the exercises I'm going to assign to you, you will calculate. So this is one special form of expressions that you can perhaps you may actually need to calculate in the future. Something like that, right? This is just a function f sitting over there. If you need to calculate this, right? So for at each of these arrival times, before time came, something must have happened. Therefore, you are either making some profit or you are being charged a cost. And this is going to be then the total cost or total revenue you are making until time t. Right? For each customer, you are getting paid or you are paying something. Right? Something like that. This happens to be, what was it? Lambda SDS from 0 to t. What did I say? Where is lambda? Okay, f of s ds from 0 to t times lambda. Okay, it's a nice, interesting formula. You will once you understand how to solve this problem, you will be able to calculate this one. But this is in general a useful formula, right? I don't want you to memorize, of course, this, but just learn how to do that. Okay? And in fact, okay, maybe you can also intuitively interpret this. This says what? Whoever arrives before time t, for each one of them, you are paid this quantity, right? So at any given time, if anybody arrives, let's say, at a typical time s, if anybody arrives, then you know that you are going to be paid f of s. Right? But what is the probability that somebody is going to arrive at a given time s? Lambda times ds. Right? We said before, right? Well, we really didn't say. Did we say that? Actually, that's something to do with this conditional result, but unfortunately I erased it. You remember that if you, well, okay, I'm not gonna, I am gonna lose a lot of concentration here. But you should just think in terms of this conditional. If you are told that there are exactly n arrivals, what is the probability that there will be k arrivals in the first u units of time? You remember we said that there is a binomial distribution coming out of there? And there actually this lambda times ds also showed up. So you can actually convince yourselves that if somebody gives a fixed time s and the probability that there will be an arrival over the next infinitesimal unit of time is alpha ds, lambda ds, okay, lambda ds, and since you are instantaneously getting paid this amount, the total expected payoff you will get until time t is going to be just the integral of this instantaneous payoff times the probability that there will be an arrival. And this is also definition of expectation as well, because over any small, actually that's another topic that maybe I should discuss. So Poisson distribution itself was what? It was an approximation of the binomial distribution. We discussed it in the very beginning of the class. And Korhan was supposed to derive it in class, actually. You let n go to infinity, p go to 0 as n times p equals stays constant at lambda. Did he do that? So that's actually the same process. It was like, okay, there are two, n large means actually you are conducting independent, identically distributed Bernoulli experiments this many times, a large number of times, right? And for each one of them, the success, getting a success was p, right? In this Poisson case, what really is happening, in each of these small intervals, you are actually conducting an experiment which says, well, is there going to be a customer coming in this small interval or is there not? If a customer comes in, it's a success. If a customer doesn't come, it's a failure. Now, how many times you repeat this experiment? N times. What is n? A large number, right? So that each one of these are very small, tiny intervals. And in each one of these tiny intervals, a success is going to come with probability lambda dt. That's the lambda ds, or I should say lambda ds. So there will be one success, therefore you are getting reward, which depends on the time when you get this success. You multiply that with the probability that you get a success, which is lambda ds. if you get a failure, namely with probability 1 minus lambda ds, nobody is going to show up in the small interval. Since nobody comes, your payoff is what? 0. It is 0. So you have f of s instantaneous payoff times instantaneous payoff at time s because a customer comes, which happens with probability lambda ds. And with probability 1 minus lambda ds, nobody comes, and therefore your payoff is 0 here because you get f of s only when there is somebody coming at that time, and you integrate. You sum, basically. You sum over all these small intervals. That is in this one. Right? That's another way of saying it. Okay? But we know more than that now, right? We can actually derive these formulas rigorously. Okay, let me go back to this one. So is this clear? So this must be clear because we use just the result that we stated before. This is clear now. And Gizem just pointed out actually this generalizes to any expression of like this. If you are interested in calculating expected values of such quantity, now we will see actually this follows. Okay? We will derive this formula for this particular choice of f, in fact. Okay. Okay, what is that? So, since we now know that this equals that, the only thing that remains, okay, we also know that this is true. We can interchange the order of summation and expectation. So we only need to figure out what this value is, right? So my whiteboard is already a mess. What should I do? Ah, it's here. Anyway, okay. Let me just, let us just complete the calculation at this corner. So we have the expected value of e to the minus beta times uk. Right? Since uk has uniform distribution, first of all, whether it is uniform or not, in general, what do we know? We are supposed to calculate this this integration over the real line. Then you realize that this is nothing but du over t, as long as u is between, as long as u is in the interval from 0 to t. If this is 0, that is going to kill that one. Okay? And if you plug this in, of course, then we change these bounds from minus infinity or plus infinity to 0 or t, e to the minus beta u times, now we will just insert this in this part because we took care of that, du over t. And what is this? What is this integral? Can somebody tell me what this is without using calculus? You might remember at the beginning I said that we don't use calculus in probability. Minus e to the what? E to the minus beta? Where is t? T should appear somewhere.
Beta times t.
Minus 2. The negative number, you mean? Is this, can this be negative? No. It should be positive. You are summing up positive numbers. What does this resemble? You must have seen this integral, no? I should give more assignments, I guess, so that you will just...
Must we multiply with a beta?
This one?
Yes.
No. No. But just pay attention to my question. Yeah, 1 minus e to the minus beta. What is this? Is this familiar? F of what? Yes. F. That has a name. Now what is it? CDF. Cumulative distribution function of what? What is important? What? What is that? Exponential. Yeah. So every time when I see such an integral, I don't look this like an integral of some exponential function. I look that if I multiply with beta and then dy, I am actually trying to calculate the probability that an exponential random variable is less than or equal to t. And I usually remember this one better than anyone else. So this The cumulative, how you calculate the cumulative distribution function when you know the density, and you remember that you don't calculate but remember that there was 1 minus e to the minus beta t. Right? Why do I tell such things? Because time will come and somebody will ask you to calculate, for example, I don't know, what should I write here? Lambda to the power n x to the power n divided by n factorial times e to the minus lambda x dx from 0 to infinity. A horrible integral. What is this?
One.
Huh? Is it 1? Is it? Did I give already? Okay, maybe, perhaps. How did you conclude that?
Total probability of Poisson.
Something related with Poisson. But total probability of Poisson, you don't mean, okay, you have Poisson. Where do I have Poisson? I see. You can say that, right? This is like actually number of arrivals until time little x, right? Maybe I should use y. Or why don't I just change this t to t? So you look this one like you look this one like what? The mean of the number of arrivals until time t if x is a Poisson process with rate lambda. Huh? But you have to be careful. So this is a discrete random variable. If you are talking about the total probability, then you sum over n. Okay, this is a sum, but this is sum over t, this is sum over n. So this is 1. But this, we actually talked about this. This has some resemblance to what? Gamma, right? So you don't have to remember what gamma was, but I at least gave a clue about how you can recall that. So gamma has something to do with the distribution of, let's say, the nth arrival time. So what is the probability that the nth arrival is going to be near time t? Here, you see, if you remember the proof, then it is going to be a lot easier to really spell out the details here. What did we do in proof? We said, okay, if you want the nth arrival to happen near time t, this can only happen if you have if you have n minus 1 arrivals. This is Poisson, so probability that there will be exactly n minus 1 arrivals here equals what? So we will write the formula now. So the mean is lambda times t to the power n minus 1 divided by n minus 1 factorial times e to the minus lambda t.
Times lambda.
Now, yeah, we have to also now multiply this with the probability that there is exactly 1 arrival in the next dt units of time, right? From t to t plus delta t, or dt. Maybe I should write like this. Okay? And we discussed it several times. This has approximately the probability that lambda times dt, right? So this is supposed to integrate. If you integrate this from 0 to infinity, right? Arrival time can only take a non-negative value. So this integral, namely this integral. So this integral is the integral for this one, and this must be 1, right? So you have you know that if you come across an integral of this kind, then it is 1. Now, can you use this to integrate this?
Yes.
How can you make that happen?
We divide lambda t.
Well, let's see. It is already there.
There is
What is the value?
Lambda t.
Huh?
And there. It means
Tell me the final
there is
answer.
n over lambda t.
This is n over lambda t.
T then
T is what? T is just the dummy variable. It cannot go out of the integration. So it is going to depend. The result should be independent of t. T is just the summation. Anybody else? Can anybody see what this is?
integrate it from 1 to infinity.
We integrate from 1 to infinity.
Yes. And then subtract e power e to minus lambda t.
Are you trying to use this or something else?
Yes.
Huh? Well, here you have integration from 0 to infinity. The bound doesn't matter. What is the difference between these two? Instead of n minus 1, you have n. Is there anything else? You know, I chose a bad example, in fact. So the answer for this one is what? What is this? This is the integral. Right? So integral remains there. What is this? This is the probability that the n plus first arrival time is near t. Isn't it? Because if you just change n with n plus 1, you get n here. So therefore this is what? 1 to the power 100. 1, yes, okay. I should make it more complicated. It is 1, yeah, so n doesn't really cause any trouble. Instead of n minus 1, you have n. Right? Okay? So, yeah, you may see actually integrals from another angle if you are familiar enough with the probability density functions. Or even if you are dealing with the summations, then you may try to remember the probability mass functions. Okay, it's a small remark. An ability that you can gain only over time, I guess. Okay, now we have that. We have this value. We should perhaps write this cleanly here. So we have what? In the numerator, I have 1 minus e to the minus beta t, and you divide this by beta times t. Okay. Now we take this and bring it here, and sum over k, right? But first you, either by looking at that or looking at this, all these expectations, right? Since UK's all have the same distribution, they are all going to be the same for each k. Therefore, we have actually n times expected value of one of these uniformly distributed random variables. And why don't I just choose the first one, namely u1? So this equals that. And now we have the result for this one. So this is, maybe I should write here, this equals to what? Where was that? Over there, right? So n times 1 minus e to the beta times t divided by beta times t. Okay. Now by far, what did we do? Now we know what this quantity is, this conditional probability, right? And then we can come back to our original problem. So we said we were interested in this expected present value, which we wrote as what? We first conditioned on the number of arrivals, and then we know the answer for this part. Okay, we can write this again if we really need it. So we will just plug that expression into this formula. So for this we have n times 1 minus e to the minus beta t divided by beta t. And let me first leave this as it is. Now, in this expression, right, this part doesn't depend on the summation n, so we can take that out. Then you are actually summing over n of what? N times the probability that x equals x t equals m. What is this sum? What is this sum? N times? Okay, if n were not there, it is 1. Because you are looking at the total probability. N times the probability that xt equals, xt takes the value n. So that's expectation. So this is a constant, doesn't depend on n, times then the expected value of xt. And do I know what this is? Do we know what this is? Xt was what? Poisson distributed random variable with mean t times lambda, right? Lambda is supposed to give you the expected number of arrivals per time unit. Per time unit. Now you are calculating, here you are calculating the expected number of arrivals over the time interval from 0 to t, which has length t. So we multiply t, length of the interval, with expected number of arrivals lambda per time unit. Right? So this is therefore lambda times t. Okay? And then t's will cancel. You have lambda over beta times 1 minus e to the minus beta t. Okay? So this is now the expected present revenue you expect to get from that bridge that is being considered to be built, right? If it is more than, let's say, how much you expect to pay to build that bridge, then maybe it is a good investment. If it is less than, then you don't build that bridge. This doesn't take into account how much environmental hazard you are giving, right? Somebody should actually give or just put a course on such things as well, so that industrial engineers are not totally motivated by profit. Is there such a course at Bilkent? Right? Environmental engineering or something like this? But at least you should know. You know that you should actually worry about such things. Okay. So this was one, right, illustration of this result. We haven't shown yet why this is correct, but let can still wait. Let us look at another example. Another example. Okay, this is exercise 4.5 in chapter 5. Okay. And I guess in this question we are interested in the probability that a system is going to be empty at a given specific time. Okay, so exercise 4.5 from our textbook, and it is, I guess, on page 309. Okay. Now customers arrive at a certain facility according to a Poisson process with rate lambda. Okay. And each customer who entered the system spends a time in the store that is a random variable and exponentially distributed with some given parameter alpha. Okay. So we know how much time they will spend in the store. Exponentially distributed. We have also a distribution for that. Okay? And then the time that each customer spends is also independent of how much time the other customers spend. So these are not like the hertz, so they don't move together. Okay? They come in and just spend some time and then they leave. And we would like to find the probability that the store is going to be empty at the end of, let's say, 1 hour. Or I'll make it, we'll just study for a general t. Okay? So what is the probability that the store is going to be empty at time t? Okay? So what is the problem? So people are coming and then some leave, some other comes in. So at time t, what is the probability that we will find the store totally empty? Okay? That's the problem. Okay? So, okay, let's again denote by xt the number of customers. Okay, number of customers, not in the store actually, arriving to the store until time t. Okay, till time t, and then what should we do? we know that, right, x, which consists of random variables xt for each t, is a Poisson process. It is in fact homogeneous Poisson process with rate lambda. Okay. Right. And let us denote by, okay, let me first denote by W1, W2 as before the arrival times. Soon we are going to need them. And then let me also denote by Y1, Y2, and so on, times spent, okay, by these customers, okay, in the store. Okay. So this is the time the first customer spends in the store, this is the time that the second customer spends in the store, and so on and so forth. So what did we learn from the question? All these Y1, Y2, and so on and so forth are independent and identically distributed. Okay? The customer spent, or the time spent by a customer is independent of the time spent by the other customers. And we are also told that they are exponentially distributed random variables. So they are IID, exponential random variables, with some known mean. With mean, I guess, 1 over alpha. Okay? And we would like to know what? We want the probability that the store is empty at time, let's say t, capital T, a fixed time. Of course, this is not the same as this, is it? Why?
There can be some customers that comes and goes.
It comes and goes and comes and stays, everything. So this counts just the number of arrivals, right? Number of arrivals equals 0, of course, just will ensure that there are nobody, because nobody came in, right? But this is more than that. So people may come, and they may or may not leave the store. That will change the picture, okay? So we want to calculate this one. Why don't we calculate this probability after we give a 10-minute break, okay? And we are back, then we'll discuss that.